Hey guys, welcome to 9.4, comparing geo and arithmetic sequences. So the first thing we're going to do is warm up by reminding ourselves of what makes them geometric as compared to arithmetic. So in the first example, it says consider these two different sequences. List all the things you know about each. So in this case, we know right away that this one is very likely to be arithmetic because we've seen this pattern. We know that this is our a of n equals d times n plus a of 0. So we can conclude that d is the common difference, a of 0 is 3, and we could list a few numbers in the pattern. So if we wanted to plug in like the number 1, for example, if we plug that in where the n is, we would get 2 plus 3 is 5. And we could continue with this and see that the second term would be 2 times 2 plus 3, which would be 7. Now over here, this one hopefully looks familiar, but this is going to be a geometric sequence. The reason we can tell that is because we have this exponent here. The rule for geometric is a sub n equals a sub 1 times r to the n minus 1. The only difference with this one is we don't have that n minus 1 rule, but it's still going to be geometric because it's going to increase by a multiplication factor each time. So for this one, we could conclude that our a sub 1, it's actually not going to be 1/2, because for this one, if we plug it in, it's going to be 3 to the 1 power, which is 1/2 times 3, which is the same as 3/2. So that's the first term, and then we could continue with that. But the second term, we would notice, is 1/2 times 3 to the second power, which is 1/2 times 9, which is 9/2. It's still increasing by a factor of 3, so we know that our rate is 3, and then these would be the first two terms. But this would be geometric. So here's the next thing. It says, sequence is a pattern of numbers. Consider the following and decide if the sequence is geometric, arithmetic, or neither. In this case, notice here, it's 5 plus n squared. We haven't really seen one like this. So we're going to find the first 5 terms. This would be 5 plus 1 squared, which is 5 plus 1, which is 6. If I do a sub 2, I would have 5 plus 2 squared, which is 5 plus 4, which is 9. Then I could do a sub 3, which is 5 plus 3 squared. 5 plus 9 is 14. And right now we're probably going to notice that the pattern is not consistent. To go from 6 to 9, that's plus 3. To go from 9 to 14, that's plus 5. It doesn't have a consistent pattern that we're either multiplying or adding to. So in this case, it's going to be a neither. It's not geometric or arithmetic. But we'll continue because we want to list out the rest of the terms. So the next one would be a sub 4 equals 5 plus 4 squared, which is 5 plus 16, and that is 21. And then we got a sub 5, 5 plus 5 squared, which equals 5 plus 25, which equals 31. So the first 5 terms are 6, 9, 14, 21, and 31. All right, moving on to the next part here. Find the first 7 terms of this sequence. A sub n equals a sub n minus 1 plus a sub n minus 2. This is kind of a new topic. We haven't seen this notation before, but what this means here, this is the previous term answer when it's a sub n minus 1. So then the answer after that would be the answer before that. So the next thing that we're going to see here is that we have the first 2 terms. We need to be given the first 2 terms because this is going to be our a sub n minus 2, and this is going to be our a sub n minus 1, because this is going to be the very first term right here, and this is going to be the second term. So to do this rule, we would fill in a sub n, not a sub n, but a sub 1 is 1 itself, a sub 2 is also 1. So then a sub 3, we would take each of these, we would take this one, that's what gets substituted in here, and we take this one, that's what gets substituted in over here. Actually, that's the wrong order. Technically what I'm doing is taking this one, it's going into the -2. This one is going in right here. But we end up with 1 plus 1, which is not 3, 2. And then a sub 4, to do that, we would have to take this term here and plug it in over here. And then we would also have to take the answer here and plug it in, which is 2. And we get 1 plus 2, which is 3. Now I'm going to continue this pattern here. A sub 5, you have to take the 2 previous answers, so I would need to take my a sub 3 plus my a sub 4 answers, which are 2 plus 3, and that gives me 5. And hopefully you're kind of catching on. You just have to add the 2 previous terms to get that. So then the next one would be 3 plus 5, because we got to take the 4th and 5th terms, which gives us 8. And then a sub 7 would be 5 plus 8, which is 13. And if I listed these out in order, 1, 1, 2, 3, 5, 8, and 13, this is a very special sequence of numbers. If you recognize this, this is called the Fibonacci sequence. All right, the next thing we're going to look at is state the type of sequence and write the rule for the nth term. Oh, also I should have listed this up here. We kind of talked about it, but both of these sequences here would be considered neither because they are not consistent multiplication or addition factors that they change by. Okay, here's the next one. It says state the type of sequence and write a rule for the nth term. So this first one we would leave as 1, 1/4, 1/9, 1/16, 1/25. Hopefully we're catching on here, but it looks like we're increasing by a factor that's like a perfect square each time. So this is not going to be geometric or arithmetic because we're not multiplying or adding consistently. So this would be neither, but we can still write the rule for it. Since the top is not changing from here to here, we can write a rule like this. We could say that it's always 1 on top because that hasn't changed. And then technically this first one is the same as 1/1. So if we just think of this, and those are perfect squares, as squaring the n value, this should work out. So for the first example, if I do a of 1, that's 1/1 squared, which is the same as 1/1 or just 1. A sub 2 would be 1/2 squared, and there we see the perfect square, 1/4. And it would work for the rest of them, but that would be our rule for this sequence. The next one is a little bit different. It's kind of a combination. It's actually more of a geometric sequence because we are multiplying consistently. Here we're going times 5, times 5, times 5, but the 2's are staying consistent. So this is times 1. That's how you keep the pattern the same. Okay, so then our rule on this one, since we're going from 2/5 to 2/25, and it's 1 on top, 5 on the bottom, this is just your standard geometric rule, where the first term is 2/5, the rate is 1/5 to the n minus 1. And we could say that that is geometric. All right, here's our next problem. It says decide whether the word problem represents a geometric or arithmetic function, then write the function formula. So a library has 8,000 books and it's adding 500 more books each year. Since this one is adding, that's the key word, that tells us that it's going to be arithmetic. We do want to think about how many books the library currently has because our rules for how we start out here, since the library has 8,000 books, it's kind of tricky because when we add 500, that is the new year. So we can actually assume that for our starting year, our a sub 0, that is this 8,000 here. And then when we're adding 500 more, actually, no, I'm saying that wrong. The year prior, this, like the first year that we have is going to be the 8,000. This is our a sub 1. So we would actually have to work backwards to get our a sub 0 still. So this one we would take 8,000, excuse me, minus 500, which would be 7,500. So then the rule for this one would be 500n plus 7,500. So the first year, we have our 8,000, and then each year after that, it grows by 500 more. This one, however, is a little bit different. It says a gym's customer must pay $60 for a membership plus $2 for each time they use the gym. So you have to imagine that we pay our $60 up front, but then even the first time that we're going, we still have to pay 2 more. So this would be our A sub 0. Regardless if we go to the gym or not, we still got to pay that $60. So in this case, our formula would be 2n plus A sub 0, which is the 60. And that is going to be arithmetic because we're adding in between each term. So the very first time we go, technically we're going to pay $62 because we had our $60 membership and then 2 for every time we use it. The next one says a bank account starts with $10. Every month the amount of money in the account is tripled. The word tripled is going to be a rate because it's multiplication, and that's going to be R equals 3, which means we're doing geometric here. So this formula is going to be, our first month is $10, so that's our A sub 1. So it's 10 times 3 to the n minus 1 power. And moving on to we're almost to the end here. Yeah, both of these examples are very similar to each other. It says Mrs. Johnson is growing bacteria in the lab. She has 2 cultures that are growing as follows. The culture began with 10 bacteria, and each hour the culture increases by 2. This is going to be arithmetic if it's increasing by a common difference. And then the culture began with 5 bacteria, and each hour the culture doubles. That's a rate, that's a multiplication factor. So that's going to be geometric. All right, it wants us to write an equation to represent each culture. So I'm just going to divide this up. I'm going to say culture 1 and culture 2. So the first one, we already said it's arithmetic. The culture began with 10 bacteria, and each hour the culture increases by 2. So then we would think of the A of 1 would be 10, so we do need to work backwards on that one. And then our A of 0 would have to be 8 if we take away 2, and the common difference is 2. So then our rule for this one would be A sub n equals 2n plus 8. For the second one, this one would be our A sub 1 is 5. That's how we're starting. And then each hour doubles, so that is a rate of 2. So then this one is A sub n equals 5 times 2 to the n minus 1. What type of function represents each culture? We already noted this up above, so we can just recall that the culture 1 was arithmetic and the culture 2 was geometric. And then how many bacteria will be in each culture after 2 hours and then after 5 hours. So it wants us to compare 2 different terms and just see which one's going to grow faster. So I'm going to find, you can assume that this is the culture 1, this is the culture 2. So let's go ahead and find the 2-hour term, which would be A sub 2. A sub 2 is going to be 2 times 2 plus 8, which is 4 plus 8, which is 12. And then A sub 5, after 5 hours, would be 2 times 5 plus 8, which is 10 plus 8, and that is 18. So we're not drastically increasing there. The other side, it's going to grow much faster because we're multiplying. So the second hour would be this formula over here. 5 times 2 to the 2 minus 1, which is 5 times 2 to the 1 power, or just 10. So the bacteria in the first couple hours, it's actually more for the arithmetic. If I label these. And then this one is bacteria. Now watch how much it grows after 5 hours though. So if I do 5 hours, that'd be A sub 5 is equal to 5 times 2 to the 5 minus 1. 5 times 2 to the 4th power, and 2 to the 4th power is 16. 16 times 5 is 80. So we can just see that it is drastically different as compared to the other one, that it grows that much faster when it's geometric. Okay, let's go on to our last problem here. Bill is starting a coin collection. He has 2 collections that are growing as follows. The collection began with 8 coins, and each month the collection increases by 5. Again, we got that increases by 5, so that's likely to be arithmetic since it's consistently the same difference between the two. And then the second collection began with 5 coins, and each month it doubles. So we're going to see another factor times 2. So to write an equation to represent each collection, so I'm going to do C1 over here, C2. It's going to be a similar idea. We just have to make sure to note that our collection begins with 8. So that's our a sub 1. So if we need to go backwards by 5, then the a sub 0 would be 3. So this rule would be a sub n equals 5 times n plus 3, because we got to do 8 minus 5. That's how we get our a sub 0. Okay, and then our collection 2 would be a sub n equals, we're starting with 5 coins. It's doubling to the n minus 1. So that would be our rule here. So the C1 would be arithmetic, and the C2 would be geometric. And then it says how many coins will be in each collection after 2 months and after 5 months. So very similar to what we just did on that last one. I'm just going to find the a sub 2, the a sub 5 for each of these. So this would be 5 times 2 plus 3, which ends up being 13 coins. This one would be 5 times 5 plus 3, which is 28 coins. The other side would be a sub 2 is 5 times 2 to the 2 minus 1. And that's 5 times 2 to the first power, which is just 10. And then the last one here, a sub 5 would be 5 times 2 to the 5 minus 1. We just saw this earlier. It's 5 times 16, and that just ends up being 80 coins. Okay, so just kind of a continuation of comparing the two, contrasting, but noticing that they do have some similarities. We just have to be careful when we're finding different pieces. And it's just kind of more of a review and practice of what we've already seen with the geometric and arithmetic.